Good afternoon. Thank you everybody for showing up, esteemed colleagues and professors. My name is Robert Iwanaga. I am with Go With The Flow. We are on the Formula SAE team. The purpose and the abstract is to build a engine intake manifold to increase the power on the Formula SAE car, which we are building for the second year in a row now. And we are going to utilize a Helmholtz resonant effect frequency to artificially supercharge the air coming in to the intake cycle event within a certain narrow RPM band of 9,000 RPMs. So we have myself. I have taken care of the simulation, design, and testing. Brian Rogers, enjoying his beverage here, is our team leader, CAD modeler, and motivation. We have Zane Green here with a couple of his friends. He's taking care of manufacturing, administration, and he has been our webmaster. And finally, we have Dylan, who has been taking care of outsourcing and implementation. Our advisor is Dr. Richard Cohen, who has vast experience with the Formula SAE team, as well as the undergraduate and AVET coordinator. So today, what we're going to talk about is the project, the motivation for our project, some of our design constraints and of the cost. We're going to have a project overview and our goals. Then we're going to talk about some of the challenges that we've had to face and overcome and learn from. Finally, we're going to talk about the approach and the results we've had, followed by the implications of the success, wrapping up with the schedule that we've had. So again, the project is to produce a intake manifold. This is our prior design here from the 2012 car. There was really no engineering that went into that. We just made it really fast in order to be able to compete in the race that year. So that's where we started. So our motivation was to release clearly untapped power and efficiency over last year's car, where we peaked out at 37 horsepower at 9,000 RPMs. We would also like to increase our trend of increased ranking in the Formula SAE event in Michigan. We went up 20 spots from the last year. And we would also like to establish a continuous, uninterrupted Formula SAE legacy for future students at Temple University by demonstrating excellence amongst the world's preeminent engineering universities in a global arena. So the constraints and cost, the major constraint is all of our air has to pass through a 20 millimeter restrictor, which you can see at the top of the cone there. So that limits our flow. As soon as the flow goes supersonic, it chokes, and that is the maximum amount of mass airflow that we will have. Another constraint we had is developing a geometry that fit within the engine bay and the geometric constraints of our vehicle. Also, the intake had to be physically robust and rigid. The engine is experiencing extreme vibrations and also some slight forces when we change direction rapidly and so forth. As far as the cost, most of it was on the 3D printer. So we used 3 cartridges at $250 a piece, plus miscellaneous hardware totaling $800. A lot of the development went into the actual simulation and testing. Although manufacturing was also very difficult because we did experience problems with it cracking in certain spots. So this is a project overview. We started with last year's intake. We analyzed it, performed some CFDs and some data acquisition. Then we went down and redesigned it, prototyped it, checked to see how it flowed. If it was reasonable with what we were expecting, we went forward. If we experienced anomalies, then we took a step back, and then we moved forward with the final prototype, field testing, and the final design. So our goals are closely aligned to our motivation. We are motivated by our goals, as all people should be. Our main goal is to increase power production at our targeted RPM of 9,000 RPMs by 20%. Of course, to continue the trend of increased ranking at the Formula SAE team event, and to work as a team to realize a common goal for both the College of Engineering and the student body as a whole. Major challenges, first off, would be configuring an accurate CFD model which represented the real world, which is highly contingent upon the boundary conditions which we placed upon the CFD model. Also manufacturing a robust manifold. As I mentioned before, we had problems with it fracturing. It's a very brittle material. Getting the water brake dyno to work is an extreme challenge. It was in a state of disrepair, and I will talk about that a little more in the future. And also, we had to analyze and interpret the physical test data. We were getting some anomalous readings, which we had to figure out, which I will talk about again further. And of course, the physical packaging and the always unforeseen mechanical issues. So the 2012 intake analysis started with a dyno pull that we took at AWE to determine our max power because our dyno is inoperative. Then we determined the theoretical upper limit given the max airflow rate and stoichiometric chemical balances in the heat of combustion. Then we performed the CFD on the 2012 intake to see exactly what the flow characteristics were, and we also performed physical bench testing and flow testing on the 2012 intake. And based on all this information, we were then able to set realistic design goals. Test data analysis, as I said, we took a dyno pull at AWE, performed the theoretical power calculation based on the air flowing through the engine, and we measured the actual air flowing through the engine and through the runners, both at the restrictor and at the runners. So this was the picture of the dyno pull we took at AWE over the summer, and as it's stated here, we have 37 at 9,000 RPMs, which again I've said multiple times. Okay, so then what we had to do is say, okay, how much air is this moving, and based on the amount of air, how much power can we make? Because we know the chemical equation, we know the heat of combustion of fuel, we know the Carnot efficiency, and we can estimate the approximate mechanical efficiency given the Carnot efficiency, because we're losing some in friction losses, irreversibility, and drivetrain losses. So given 143 meters per second through the restrictor, heating value of fuel, again the Carnot efficiency, stoichiometric ratio, we were able to convert the air flowing through into usable work. So we got an approximate value of 57 horsepower. So given we were only making 37 horsepower, we're only making about 64% of what we believe is realistic and reasonable. And that was due to the poor airflow of the old intake. So we set a goal of a 20% increase to 84%, so that would bump us up to about 45 horsepower. This is a CFD on the old intake. As you can see in the first and second cylinders, we're experiencing vortices, and there's not as much mass airflow flowing through as the last two cylinders. As the air comes in, it's coming at extremely high velocity. It shoots by these two cylinders and then is forced back to the back two cylinders. And it's interesting because this cylinder actually was 100 degrees C less than the other remaining three cylinders. So we knew that that cylinder was being starved for air, which would contribute to an extreme loss of efficiency that we observed. This is the chart that we did. I made a manometer here and I measured the airflow going through each one of the runners. And based on the airflow, I was then able to calculate volumetric efficiency. And the red line, the trend line, is theoretical, and the blue is the actual measure. So you can see for most of the part we're under it, and then we're right around 100% at 8,000 or 9,000 RPMs, where we were making our max power at AWE, which so that confirms AWE's readings. And also you can see here the actual height of the water in the manometers. There's extreme differences in the heights, which again would lead to uneven air distribution and having some cylinders starved for air while others are running very rich, very lean. Okay, so first thing we did is determine some of the suitable geometries. So we were concerned with two things: high velocity to increase airflow rate, and also even distribution. So the one design, the dual conical, or the dual plenum here, what this is it has one plenum on top and another on the bottom, and they're connected through a small slit. So the hopes here was that it would distribute most of the air that's coming in fast into the first two cylinders, and the remaining air would be forced into the rear two cylinders. However, this is contributing to a lot of turbulence, which we wanted to avoid. The second one we used was the conical upright. This is a very symmetrical design, and it's very streamlined, so there's not any changes. There's minimal changes of direction for the air, robbing flow energy and head loss from the flow. So we decided to go ahead and CFD some of these. So this is the CFD we did on the dual plenum, and as you can see, we have good airflow to the rear cylinders, but again, we're experiencing vortices and reduced flow velocity in the first cylinder. So given the fact that this didn't produce what we wanted, and we were still getting the vortices and low flow through the first cylinder, it really didn't accomplish our goal. The second CFD we did on the conical upright showed extremely high velocity, very even velocity, very even distribution. So that was the design we went with to even out the flow and reduce head losses in the flow. So another thing we want to do is optimize the runner length to utilize the resonant effect of the air pulses traveling up and down the runner. So as the intake valve slams shut, the incoming air bounces off of it, returns up the runner, hits the open cavity of the plenum, and then proceeds to bounce back down the runner. If we time it properly, based on the width and geometry of the engine, we want to have that incoming wave front meet the intake valve just as it's opening to gain that artificial supercharging effect. So this is the formula that we used. Given the target RPM of 9,000 RPMs, the engine geometry, we found that the ideal runner length was around 11 inches for our 9,000 RPM target range. This is a CFD that we did on the intake, and as you can see, the first event here was when the engine is initially started in the CFD model. So it comes in, and this would be the natural pulse. So right around here, the intake valve shuts, the wave front travels up and down the runner, and right around this point, the intake valve is opening as the wave front is coming back down. And as you can see, the peak is both higher and wider, which would indicate more mass airflow rate if you were to integrate the area under the velocity here. Or if you were to integrate the area under the curve, you would show a greater volumetric efficiency. So given the CFD simulation reinforced and backed up the theoretical calculations, we decided to move forward with prototyping. And so this is the model we have here. It's on the desk. And this is, again, we put it back on our engine bench and with our manometer set up to flow test it. So as you can see here, this is the trend line of theoretical. The blue is the actual measured value. And you can see here it peaks right around 10,000 RPMs. So we're only off by 9,000 RPM, so that's still in a range which is very reasonable for racing. So we decided to go ahead and stick with it. It was pretty good. And compared to the old intake, you can see there's an extremely large jump right around the target range. At this time, I would like to inform you that we did get some anomalous readings. I was getting readings for about 300% efficient, volumetric efficiency-wise. I knew that was wrong, so I consulted with Dr. Cavallo and Dr. Cohen, and we reasoned that due to the inertial effects of the water and the response time of the manometer as a sensing device, the high-pressure wave front forced the water up higher, but before the water had a chance to return to an average level, the next wave front was coming in, forcing it up again. Because at 9,000 RPMs, you can imagine there's 150 wave fronts coming in, or 75 wave fronts coming in per second, because it's a 4-stroke every 2 cycles. So, the implications of the success. Obviously, increased power and efficiency gains. This is good because it will increase our dynamic standings. Not only that, this technology can then be taken from the racetrack into the street to improve the performance of vehicles that all of us drive, which would help to ease some of our fuel and emissions problems that we're experiencing today. Furthermore, validating the CFD model implies that we can go back and use this model to pull even more data and get more detailed results, and possibly even alter it to reflect changes in the real world. And what that would do is it would cut out time of manufacturing. Knowing that our CFD model is accurate, we can then go back and use that to pull data and just completely bypass some of the more laborious and time-consuming prototyping. Again, improved FSAE dynamic event results would increase our standing, and that would give us enhanced recognition and an enhanced reputation for Temple, again in a global arena with some of the other Formula SAE teams, of which we compete with these teams from around the world, some fairly preeminent universities. So this was our schedule. Our original schedule is in blue. The red schedule is what actually happened. So we ran a little bit over on the majority of the events. However, being that this is the first time the 4 of us operated in such a way together, I thought we were reasonably within a good target for our proposed time range. So as you can see, we ran a little bit over, but we're still on schedule, completing all of our assignments within a reasonable time frame. So in conclusion, our CFD model was confirmed by the physical test data. The flow bench data indicates an efficiency of 125% at 9,000 RPMs, and approximately 90% across the rest of the range, which would then translate over into our 20% increased power at our target RPM range. Unfortunately, the water brake dyno is still inoperable. We were not able to get that up and running. I could use many descriptive words to describe the problems we had with it, but we'll just have to settle with it as a problem. So what we're going to do is, once we have the car up and running and ready for competition, we're going to reschedule an appointment with Dane, who is a Temple Formula SAE alumni, and he's going to go ahead and let us re-dyno the engine at his facility, AWE, and then we will have that in our final design report. Question?
What kind of redesign did you do on this after you tested it?
After we tested it, we were extremely pleased with the geometry that we had. However, when we went to put it in the vehicle, one of the problems and the design constraints we had was fitting it within the physical packaging of the engine bay area, because there are rules that the Formula SAE organization puts out that it has to be within a certain envelope, and unfortunately we exceeded that envelope. So what we did is we added these bent runners to sort of move the intake back down into the engine bay area. It worked fairly well. We're still getting the final tweaks of the packaging worked out. It did elongate our runners somewhat. However, given that the physical benched data indicates our peak power at 10,000 RPMs, and we originally targeted for 9, by elongating the runners, it actually gives the wave more time to travel back and down, which would correlate to a slightly lower RPM. So we thought that that was a fairly good compromise, because the alteration actually moved us back into our original target window.
And do you have a prediction for what power this new intake will give you in the engine?
I do have a prediction. I did not do the calculation, but we can go to this slide here. So given the flow that we were measuring on the physical bench at 9,000 RPMs, I can go ahead and re-back calculate, given you know, the stoichiometric chemical equation, heat of combustion. So knowing how much air is flowing through the engine, the Carnot efficiency, and the irreversible losses, I can actually calculate that. However, at this time I do not have that data, but it will be in the final design report.
And inside the cone, at the base of the cone, it's just flat with circular holes connected to the.
It is flat right now.
Yeah.
We have.
That's good enough.
Yeah, we have designed. We have a cone and insert designed, which we don't have with us, but to help funnel the air in. But again, it's a little bit it's a little bit hard to predict. So we're going to have to actually physically test it with and without the insert.
That insert's down at our post then as well if you'd like to see it.
Your engine has 48 HP. Power of the engine.
Over last year's car had 37 horsepower. We don't. The dyno is inoperable still, so we don't actually have hard numbers. All we can do is approximate it, giving the airflow rate. But as soon as we get the engine up and running, we're going to take the car back to AWE, do a dyno pull on it, and make sure that's in our design report, the finalized design report.
Did you get this engine from
It's a salvage engine. It's a salvage engine.
So did you make some improvements?
To the internals of the engine? No, unfortunately, we did not. We had many things that we wanted to do. That would have been nice. We wanted to deck the head to increase the compression ratio and use a higher octane fuel, and also port and polish the heads. However, given the scope of the project, we had to make compromises. So we thought it was better to actually get a vehicle running there as opposed to taking the engine apart and risk having something go wrong. We wanted a car to compete with, you know, and these are developments that hopefully the Temple engineering students can make in years to come.
Thank you all for coming.